Hi guys, my name is Tze Lynn, and today we are going to learn about total internal reflection. Let's start. So first, what is total internal reflection? We look at this picture, we can saw that there are two fish in this picture. One is object and one is image. This is caused by the total internal reflection. Okay, total internal reflection only occurs when light travels from a medium of high optical density to a medium of low optical density. And these are some examples about the light rays traveling from glass to air for three different angles of incidence. We look at the first one. Okay. When the incident angle is less than critical angle, the light rays will refract away from the normal. So the light ray will refract away from the normal, and a weak reflected ray can also be detected. Okay, this situation only occurs when the incident angle is equal to critical angle. So we look at this explanation. When the incident angle is same as the critical angle, the refracted rays travels along glass-air boundary. Okay, we look at this diagram. We can see the light ray is just travels between the air and glass. Okay, and a stronger reflected ray can be detected. Okay, next one is when the incident angle is greater than the critical angle, there is no refracted ray. Okay, no refracted ray here, but the total internal reflections happens. Okay, so we can see the totally reflected ray at here. Just now I have mentioned many times about the critical angle, and this one is the meaning of the critical angle. Angle of incidence in the medium of high optical density, when the angle of refraction in the medium of low optical density is equal to 90 degrees. Now we learn this formula. This formula will help us to calculate the refractive index or the critical angle. Okay. If the refractive index of diamond is 2.42, then the critical angle for diamond can be calculated. Sin C equal to 1 divided by 2.42. Okay, then we will get this value. After that, we throw the sign to the opposite side of the equation. Sin -1 multiplied with 0.4132, and we'll get the answer, 24.4 degrees. Okay, the critical angle for a medium depends on the optical density of the medium. The higher the refractive index of a medium, the smaller the critical angle of the medium. It means that the critical angle is not a constant value. It will change, depends on the optical density. So the higher the refractive index, the smaller the critical angle. Now, we look at the natural phenomenon that involves total internal reflection. Okay, this one is formation of rainbow. When the white light from the sun enters the water droplets, the light will experience refraction and disperse into different colors. Okay, so we can see there are many colors here: red, orange, yellow, green. Okay, more and more. And All these different colors experience total internal reflection on the surface of water droplets. Okay, the light rays reflected experience refraction and dispersion again when move out from the water to air. Okay, move out from the water to air here. And lastly, the colors of the rainbow are seen by the observer. Now we will watch a video about the mirage. So please pay your attention.
What is a mirage? An invisible cloak. Mirage is an illusion in which it appears as if there is light present on the plane.
Okay. Okay, now we look at the explanation of the mirage. The layers of air above the root has different optical densities. Okay, the layer just above the root is hotter than the upper layer. So here is hot air and here is cold air. Then the hot air has smaller optical density than the cold air. So when the light travels from the upper layer to the lower layers, it will refract it away from the normal. When the angle of incidence is greater than the critical angle, the total internal reflection occurs. So when it reaches here, the total internal reflection occurs. Okay. Then the light will refract towards normal again, back to normal again, and reach the eyes of observer. The observer will see the image of a cloud as a puddle of water on the road. Okay, next one. We look at the applications of total internal reflection in daily life. And first one is prism periscope. The prism periscope is used to look the object that behind the obstacles. Okay, so how it works? First, the light will travel into the prism without any refraction when it passes through the AB sides. Then it will reach the AC side. When it reaches the AC side, the total internal reflection will occur because the angle of incidence is greater than the critical angle. Therefore, the light will bend downward. Okay. Then the lights will travel along here and reach here. Same, it won't happen any refraction when it passes through the DE side. But when you reach the DF side, the total internal refraction will occur again, and the light will emerge out from the EF side and enter the eyes of observer. Okay, the image form upright and same size as the object. Okay, we will watch a video about the optical fiber.
Internal reflection is important in technology. A lot of communications are done, including telephone and other communications. You may have an optical cable in your home stereo or home theater system that communicates audio information through an optical cable. The principle is total internal reflection. If we come in at a glancing angle, then all of the light that's incident on this surface and on this surface will be reflected back internally into the material. So it works for glancing angles, and the beam needs to be confined within a material that is more optically dense, has a higher index of refraction than the surrounding material. But any shape will do. So a rectangular shape here, you can use a circular shape, confining all that light inside of that fiber. Now this is a more typical, optical cable or light fiber. I'm just going to introduce the beam here. You'll see it come out on the far end. This is an example of we have a source of light at the base here, and each of these, all our strands of plastic, and they are channeling the light through them. And they can be bent or whatever, and they still channel that light. There is a certain radius. If you kink it really hard, then that brings you away from the total internal reflection, and you lose the effect. But very effective, very important in today's technology, total internal reflection.
Okay, now we look at the optical fiber. The optical fiber is usually used in telecommunications. Okay. The inner cord, which has a high refractive index, is surrounded by a layer of cladding with a low refractive index. So the inner cord has high refractive index and the coating has low refractive index. So it causes the light can occur total internal reflection inside. Okay. The light signals enter one end of the optical fiber here, and experience total internal reflection continuously until it reaches the other side of the end. Okay. As such, signals can be sent rapidly without disturbance from electrical signals. Okay, now let's do some exercises. The first question, figure 6.25 shows a light ray traveling from air to a prism with refractive index of 1.49. Calculate the critical angle of the prism and complete the path of the light ray until it exits the prism. Okay, so to calculate the critical angle of the prism, we need to use this formula. Okay, sin c equal to 1 divided by n equal to 1 divided by 1.49. Then we throw the sign back to the opposite side of the equation. Sin -1 multiplied with 1 divided by 1.49. And we get the answer. Critical angle of prism equal to 42.2 degrees. Okay, now we look at this diagram. In figure 6.2, angle of incidence I equal to 45 is larger than the critical angle C equal to 42.2 at sides AB and AC. Total internal reflection happens and light ray emerges from the sides of BC along its normal. So it means that the light travels from here and it reached AB. Then the angle of incidence is larger than the critical angle. So the total internal reflections occurs and the light reflect to here AC sides. When you reach the AC sides, the total internal reflections occurs again. Then the light emerges from the sides BC along its normal. Okay, the next one is figure 6.27 shows the path of light rays traveling through optical fiber from NA to NB. Explain the change in direction of the light ray at points Q, R, S, T, and U. So when the light travels from here, it will reach the point Q. At point Q, the refracted light bends toward the normal, okay, and reach point R. At point R, S, and T, the total internal reflections happens. Lastly, it reached the point U. The refracted light bends away from normal. Okay, the next question. If the refractive index of the optical fiber is 1.51, determine the value of angle X. To calculate the angle X here, we need to use this formula. N1 multiplied with sine delta 1 equal to N2 multiplied with sine delta 2. Okay, we put the value in it. 1 multiplied with sine 45 degree equal to 1.51 multiplied with sine X. Then we calculate it by using the calculator. And lastly, we'll get the answer 27.9 degree. Okay. C. Why must the material of optical fibers be of high optical purity? High purity materials allow the critical angle along the fiber optic to be consistent. All signals which enter the fiber will experience total internal reflection. Okay, let's do more exercise, okay, on practice formatting 6.2. Figure 6.28 shows the path of light which travels from air to a prism. Determine the angle of refraction of light ray in prism. The refractive index of the prism is 1.50. Okay, look at the solutions. We use this formula n equal to sine I divided by sine R. Okay. Then the sine R equal to sine I divided by n. We put the value in it. Sine 45 degree divided by 1.50. We will get 0.4714. We calculate the R. We throw the sine to the behind. Sine negative 1 multiplied with 0.4714. And we will get the answer 28.13 degree. Okay, now we'll see the next question. Will the light ray experience total internal reflection at the side AB of the prism? Explain the answer. Okay. Okay, this question has a little bit complicated, but don't be worried, just follow the step by step. First, we need to calculate the critical angle of the prism. By using this formula, and we will get the answer 41.81 degree. Okay, then we need to calculate this angle here. Okay, I have label here. Okay, by using this formula, n1 multiplied with sine delta 1 equal to n2 multiplied with sine delta 2. Then we put the value in it. 1 multiplied with sine 45 degree equal to 1.50. 1.50 is the refractive index of the prism. Multiply with sine delta 2. Then calculate it. We will get the answer 28.1 degree. Okay, now we look at this diagram. This yellow dotted line is the normal. So from this normal to the side AC, okay, look at here, from here to here, okay, is 90 degrees. And then we can look at here, the side AC from here to the red dotted line here is 45 degrees. Why? Because here is 45 degrees and these two angle is opposite angle. So here is 45 degrees and here is 45 degrees too. To find out delta 3, we need to find out here the yellow dotted line to the red dotted line to red line here. Okay, this one small angle here is same as here. Okay, so we just use 90 degrees to subtract 45 degrees and subtract 28.1 degrees, and we will get the answer 16.9 degrees. Okay, lastly, we just need to find out this degree by using this formula again, and we'll get the final answer 25.8 degrees. Then, okay, just now the question asked, is the total internal reflection occurs? The answer is no, because the angle of incidence I equal to 16.9 degrees is smaller than critical angle C equal to 41.81 degrees at side AB, okay? The light passed through the prism and refracted towards the normal line. The last question. Figure 6.29 shows a fine optical fiber made up of inner core which has a high refractive index surrounded by caving material of a low refractive index. Determine the critical angle of the optical fiber. Then, what is the advantage of fine optical fiber? Now we look at these solutions. To calculate the critical angle, we just use this formula. C equal to sine -1 multiplied with 1 divided by 1.80. And we get the final answer, 33.75 degrees. And this answer is for the advantage of the fine optical fiber. Okay, fine optical fiber has smaller critical angle, so more total internal reflection occurs. Polymer optical fibers are usually made up from a polymetallic metacrylate core, surrounded by a cladding made from fluorinated polymer. The material of the cladding because it has lower refractive index than the material of the core to enable total internal reflection occurs. Okay, thanks to listen to my presentations. Hope to see you guys soon. Bye-bye.